Welcome back to the deep dive. Our mission today is all about achieving, well, absolute fluency in the hidden language of the web. We're talking about that precise three-digit technical vocabulary and all the header mechanics that, govern success, failure, and security every single time you load an app or hit a button.
Or integrate an API, which is a huge one.
Exactly. We're going way beyond the superficial definitions you'd find on Wikipedia. This is the stuff that really bridges the gap between, say, a high-level product strategy, who gets what feature, and that moment the engineering team actually starts writing the code.
Absolutely. And if you, the listener, have ever spent a day or even a week struggling to debug a failed third-party integration, this is for you.
Oh, for sure.
Or if you've been stuck in that feedback loop with QA because they report an auth bug and you have no idea if that means someone can't sign in or if they can't access a specific folder, well, this deep dive is your shortcut.
It's the decoder ring.
It is. We are decoding the two central pillars of web interaction.
Yeah.
First, how resources are secured. That's the precise relationship between authentication and authorization. And second, how systems communicate the outcome of any action. And that's the vital language of HTTP status codes.
So our goal for you is to really equip you with the mental model and the vocabulary you need to communicate clearly, decisively across every single team. Mobile, web, backend, QA, support.
You're going to become fluent in that shared language.
Which is really, at the end of the day, the language of diagnosis.
It is. And we've synthesized material here that's specifically designed to give product and API professionals a practical, an actionable translation of these concepts. We are not just memorizing numbers.
Yeah.
We are understanding the diagnostic value of every response, the security implications of every header, and crucially, the product decision that has to follow every single failure state.
Okay, let's unpack this. We're going to jump right into the foundation, which, frankly, is a massive source of confusion, inefficiency, and delay.
It really is.
I'm talking about drawing a firm line between identity and permission.
The problem of vague language here is, it's just profound. Nearly every development team, especially if they're not, working strictly on security, they tend to call the whole process auth.
Just auth, yeah.
And that single term auth, it's trying to cover everything. Identity verification, password storage, token generation, role checks, access control.
And that ambiguity, it just slows everything down. It leads to vague acceptance criteria, incorrect feature implementation.
We need absolute clarity here right out of the gate.
We do. And I know it can feel like we're being a bit pedantic, but this pedantry is what saves you hours, maybe days down the line.
Exactly.
So let's start with the first half of that equation, authentication, or you'll see it written as authn. When we talk about authn, we are asking a single fundamental question. Who are you?
That's it. Authn is purely the process of verifying identity. The system needs to confirm that the entity requesting access, whether that's a person, an app, a microservice, is who they claim to be. The source material frames it perfectly. You're verifying the claim.
So think of the practical process. A user opens a mobile app, they type in a username and password. The service takes those credentials, verifies them cryptographically.
Right. Or in a corporate setting, they click an SSO button, single sign-on, and the service exchanges tokens with an identity provider.
Or maybe they're just presenting a JSON web token they got a few minutes earlier. In every single one of those cases, the only function is confirming identity. Have they been recognized?
And this is how it translates for clear, precise requirements. User is authenticated. If you write that in your criteria, it means one thing. They have passed the identity check, they have a valid session, or they're holding a current non-expired token.
And that's the boundary.
That's the boundary. It doesn't mean they can do anything yet. It just means the system recognizes them as a valid entity.
Okay, so here's where the confusion usually creeps in. Once that identity is established, we move to the second and equally crucial half, authorization or authz.
Right.
So if authn is, who are you? Then authz shifts the focus. It asks, what are you allowed to do?
Authorization determines access rights and permissions based on that verified identity. So you successfully signed in, but what role do you have? Are you an admin, a standard user, a restricted viewer?
Does your identity give you the right to modify this specific file, or can you only read it?
That's the policy enforcement layer.
A great practical example we've all experienced is, you sign into some software, you've successfully completed Auth, but when you try to access the settings page for billing, you see an error message.
Yep. The system knows you, it validated your credentials,
Yeah.
but your current permissions block that action. You're trying to view data you don't own
Okay.
or do something reserved for a higher role.
So the requirement translation follows. User is authorized. This confirms they have the necessary role or scope or permission level to do the specific thing they're trying to do. So let me play devil's advocate for a second. I know what engineering teams do. They'll use auth as a catch-all internally because it's just faster. Isn't defining both authn and authz constantly just unnecessary friction?
And that's the core tension, right? While auth is fine as an internal shorthand, the moment it results in a bug report, it loses all of its efficiency.
Okay.
Explicitly stating both authn and authz in requirements and in bug reports, it radically improves clarity and debugging speed. And that's because those two failure states demand completely different engineering responses.
Okay, give us a concrete example of that. What's the divergent response?
Well, if a user can't access a resource and it's an authn failure, that means the token is expired or missing. The engineering solution is to trigger the sign-in flow, or maybe more likely a token refresh mechanism.
Okay.
But if it's an authz failure, the engineering solution involved checking the database for the user's role, or their scope, and confirming the policy logic. You don't ask a user to sign in again just because they don't have admin rights. That would be a terrible user experience.
Right, and it prevents that frustrating back and forth where the QA team reports auth failure on the export button, and the backend team immediately has to ask, okay, did the user need to log in again, or did they just not have the export permission?
Exactly. That clarity saves hours. It transforms a vague failure into a precise diagnostic report. You need to define those acceptance criteria to explicitly handle both of those failure states differently.
So the key is shifting your vocabulary from that vague umbrella of auth to the precise language. Authentication for identity, authorization for permission.
Yes.
Okay, so moving from the conceptual definitions to the actual mechanics, let's look at how the web handles this whole challenge process, the standardized mechanism built right into HTTP for protecting resources.
This is truly the dance on a wire.
Yes.
It's this three-step flow that happens every single time a client tries to hit a protected endpoint, and it relies entirely on specific HTTP headers and response codes to communicate. If you get this sequence, you get API security fundamentals.
Let's detail that high-level process then, focusing on those communication signals.
So the process starts when the client requests a protected resource. Let's just say it's a PIV1 billing records. The server, being stateless, determines that the client either hasn't provided credentials or the credentials it sent are invalid.
And critically, the server doesn't just hang up. It doesn't send a generic nope. Instead, it sends a very specific signal back.
Right, the infamous 401 status code. And accompanying that code, it issues a specific challenge.
And that challenge is the heart of the framework.
It is. It tells the client, hey, I need credentials, and here is the acceptable, standardized way you should send them back to me. The client gets this challenge, understands it has to do something, fetch credentials, attach a token, and then it retries the request.
And then finally, the server reviews the new credentials and makes the final access decision. Success, or maybe another failure like a 403, or even another 401 if the new credentials are also bad.
That summary challenge credentials access decision, that perfectly describes the protocol.
Okay, so let's focus on those two crucial headers that transmit these signals.
The first one is the one the server sends to the client. The www authenticate header.
This header is so interesting because it only appears on a 401 response. Its entire job is to advertise how the server accepts authentication. It's the server setting the rules of the game.
Think of it as the server providing instructions for the next step. It might advertise an authentication scheme like BASIC, which means the client should base64 encode the username and password and send them back.
Right.
But more commonly today, in modern APIs, it advertises bearer, and that signals it expects a short-lived token, a bearer token, in the next request.
And its usefulness for a product manager or an integrator is immense. If you're integrating with a new API and it fails, you get a 401 right away. Looking at that www authenticate header is your direct nonverbal documentation.
It cuts right through the process of digging through potentially out-of-date API docs.
Exactly. It tells you exactly the scheme the API expects you to use.
Okay, then we have the client's contribution to this dance. The header the client sends back to the server, the authorization header.
So the client uses the authorization header to present the actual credentials. This is where those basic credentials are far more commonly now the bearer token are placed.
And the structure is almost always scheme then value. So authorization, bearer, and then this long string of characters.
And this header is the critical diagnostic tool. This is that scenario every engineer has faced. The request works perfectly fine in Postman, but it fails in the mobile app.
Yes, where I manually typed in the token.
So what's the first thing you check when you hear that?
You immediately open the network inspector and you confirm. Is the app actually sending the authorization header? Is the token formatted correctly with the bearer prefix? And most importantly, is the token itself still valid? Is it not expired? Was it not accidentally truncated by some client-side bug?
Right. If the app is missing that header, the server never even sees the credentials.
And the client is just stuck in that 401 loop, even though they successfully logged in 5 minutes ago.
So understanding these two headers, the instruction manual, www authenticate, and the delivery truck authorization is really essential.
Okay, so the headers are the mechanism. But how is that identity information, those credentials, how are they actually managed and transmitted in practice?
Right. Let's look at the conceptual ways identity is packaged today across, traditional web, mobile, and pure APIs.
We can categorize these into a few common high-impact patterns. We can start with the old guard, the approach that defined the original internet.
The session cookie.
The session cookie. In this model, which still dominates a lot of server-rendered web apps, the user signs in and the server generates a unique session ID. The server holds onto the session state, and the browser stores that ID in a secure cookie.
And for every request after that, the browser just automatically sends the cookie back, and the server maps that ID to a persistent, authenticated session.
The main benefit there is that it's inherently protected against certain attacks like CSRF, cross-site request forgery, because browsers are built to manage cookies securely.
But the drawback is it's stateful. The server has to maintain this massive store of active sessions, which can become a huge scaling bottleneck.
Which brings us to the dominant modern pattern, especially for mobile apps and scalable APIs, the bearer token.
This is the structure we see in that header, authorization. Bearer token. The key difference here is statelessness.
Exactly. Often, this token is a JWT, a JSON web token, which is cryptographically signed and contains enough information, they're called claims, about the user, for the server to verify them without needing to look up a session in a central store every single time.
And this statelessness is what enables massive scale and microservices. A request can be routed to any server, and that server can immediately verify the token's validity just based on the token itself.
But tokens introduce their own complexity, especially around managing expiry and revocation. And this is where we need to dive into a really critical product decision point in modern Auth.
The difference between the access token and the refresh token.
This distinction is crucial for both security and user experience. The access token is the short-lived credential. It's the key used for immediate access. Because it's short-lived, maybe it expires after 5 or 15 minutes, it minimizes the damage if it's ever intercepted.
But if you design your system so the access token expires every 15 minutes, the user would have to manually log in again constantly.
Which is a terrible UX.
A terrible UX.
Precisely. That's where the refresh token comes in. The refresh token is a long-lived credential, maybe it lasts for weeks or months, and it's stored securely on the client. Its only purpose is not accessing resources directly, but securely asking the authentication server for a new access token when the current one expires.
So if the app makes an API call and gets a 401 unauthorized because the access token is stale, the application's criteria should immediately say, okay, now we attempt a silent background request using the refresh token to get a fresh access token.
And the user should never even know this happened.
All right.
That's good acceptance criteria. If that refresh succeeds, the app retries the original request with the new access token, user continues seamlessly. If the refresh token itself is expired or revoked.
Maybe they changed their password.
Exactly. That is the definitive point where the system must force a full visible sign-in. Which brings us back to that 401 trigger, that decision, that graceful transition. That's a product requirement.
Now let's quickly touch on OAuth 2.0 and OIDC because they underpin most of these modern token flows. People often confuse OAuth 2.0 with being the authentication method itself.
It's a really common misconception. OAuth 2.0 is an authorization framework. It's about delegated access. It's a mechanism for securely issuing tokens to applications on behalf of a user. OIDC, or OpenID Connect, then layers on top of that to provide the actual authentication and identity layer.
So the purpose of delegated access is simple. It's enabling a user to sign in through a trusted third party, think sign in with Google, or corporate SSO without giving the application their primary password.
Right. The application receives tokens, and the crucial product aspect here is that these tokens contain specific scopes and claims. The scopes dictate the level of access the token grants, like read profile versus write data.
And the claims are verified facts about the user, like their user ID or their verified email address.
Which means that as a product manager, you have to define the required scopes for your application. If your app only needs to read a user's profile, you should never request the post on their behalf scope. Defining that minimum required scope is a critical security and product decision.
Now, despite all this technical complexity, the product manager's role in this whole domain, it often gets undervalued. Because yes, the engineering team handles the cryptographic heavy lifting.
Sure.
But the product role is absolutely critical in defining the behavior, the constraints, and the user experience around every single aspect of this.
You have to specify key behaviors. For instance, the specific login methods required. Are we supporting email password, SSO, a magic link? Each requires a different engineering effort and has different security implications.
And tying back to tokens, you need to specify not just the session duration, but that detailed token refresh behavior we just outlined. If the access token expires after 15 minutes, you must design and require that seamless, silent refresh mechanism.
And, tying back to Auth, you have to define the specific roles and scopes required for different features. A feature shouldn't even be prototyped until you know the entitlement model, who is allowed to see the button, and who can execute the API call behind it.
Exactly. And finally, the expected UX and the corresponding status codes when sessions expire or are revoked must be crystal clear. That decision isn't an engineering choice. It's a fundamental product design choice triggered by that technical response code.
Okay, let's shift gears entirely now, moving from identity and permission to the universal language of communication. HTTP status codes.
These 3-digit numbers are the immediate, silent, and highly structured communication from the server to the client after every single interaction on the web.
Status codes are truly the lingua franca of the internet. They don't just tell the client the outcome, they signal to every stakeholder, product, engineering, QA, DevOps, exactly where the failure occurred and what class of problem they're dealing with.
And the first, most valuable step to mastering them is adopting a clear mental model based on the 5 classes of response codes. The structure instantly narrows down where the root issue lies.
The classes are organized by the first digit, which dictates the severity and source of the problem.
First up, 1XX, informational. These are pretty rare and typical app logic. You might see a 100 continue. They just tell the client, hey, I got your request, everything looks fine so far, but I'm still processing.
Then 2XX, success, the most comforting block. This means the request was successfully received, understood, and accepted. Everything's working.
3XX, redirection. This tells the client to take further action, usually by requesting a different URI. The resource has moved.
4x, client errors. This is the diagnostic hotspot. It signals the request itself was flawed. Malformed payload, missing data, incorrect authentication, not enough permissions. The fault lies with the sender.
And finally, 5XX, server errors. This is the escalation signal. The server failed to fulfill an otherwise valid request. The client did everything right, but the back-end system encountered an internal fault.
And the value proposition of just understanding these classes is diagnostic efficiency. When a bug comes up, the status code immediately answers that crucial question. Is the user doing something wrong? Is the request malformed? Or are we having an outage?
It's triage. If you see 4XX, your teams immediately start checking the client state, the request payload, or user entitlements. If you see a 5XX, you immediately escalate to checking service logs, monitoring, and maybe initiating an incident response.
That structured thinking, driven by that first digit, is why this knowledge is so powerful.
Okay, let's start with the good news, the 2XX success block. While 200 is the one everyone knows, understanding the subtle differences between 201, 202, and 204 can dramatically impact how you define feature success.
The baseline is, of course, 200 OK, standard success. For a GT request, the response body has the data you asked for. Simple, I asked and I received.
But when you are creating something, you ideally want to see a 201 created. This signals success after a creation request, usually a PO host.
And that 201 is essential because it distinguishes creation from general success. But more importantly, it provides critical info for the client app. It should return the newly created object in the body, but it absolutely must also return a location header pointing to the new resource's URL.
So the client can immediately go to it.
Exactly. It doesn't have to guess or construct the URL itself.
Well, then there is the code that is critical for modern large-scale systems that deal with long-running tasks. 202 accepted.
A 202 is necessary for async jobs. Imagine uploading a large video for processing or generating a massive report. The server doesn't want to hold that HTTP connection open for 10 minutes when it works.
No.
Instead, it responds with 202 accepted, which confirms the request was valid and placed into a queue for processing, but it's not completed yet.
It's the server saying, I promise I'm working on it, and that lets the client immediately shift the user experience, maybe show a status bar or pull a different endpoint for updates.
Right, and product criteria for 202 flow have to define those state transitions, from pending to processing to complete.
And finally, 204, no content. This is also success, but the server explicitly tells the client there is no data payload in the response body.
This is typically for a successful delete request, or actions like mark as read, a password change, something that updates a toggle. The server confirms the action worked, but the client shouldn't expect to parse a payload.
And the potential pitfall here, which causes a lot of front-end bugs, is about expectations. If the client code expects any response body to trigger a UI update and suddenly it gets a 204,
it can crash.
Yeah.
Or just fail to update the screen. The PM tip here is alignment. For every 204 endpoint, the client team needs to know, should they do an optimistic update of the UI, just assume it worked? Or should they force a full refetch of the data to ensure consistency?
Okay, moving on to the 3xx redirect block. These are often handled by the browser automatically, but they carry huge product and SEO implications.
And we have to differentiate between permanent and temporary moves. A 301 moved permanently, or the safer version, 308 permanent redirect, signals that the resource has permanently changed location.
And for product teams managing content or APIs, this is critical. Search engines are explicitly told to cache this and update their indexes to the new URL. If you accidentally use a 301 when you meant a 302, you can permanently break old links.
Inversely, a 302 found, or the more semantically correct 307 temporary redirect, means the resource has moved temporarily. We see this all the time in complex login flows, like Auth, where a user is temporarily sent to an IDP and then back.
If the client shouldn't cache that response.
Right. It should keep using the original URL for all future requests.
And we can't ignore 304, not modified. This is a performance champion, essential to caching, but it is often so confusing to debug.
A 304 is triggered when a client requests a resource, but includes specific caching headers, like if none match or if modified since. It's the client telling the server, hey, I have a cached version of this resource. Here are its identifiers. Only send me the full thing if it has changed.
And if the server checks and sees the resource hasn't changed, it just sends back a 304.
Which tells the client, success, use your cache copy. And this saves a ton of bandwidth and processing time.
But the debugging confusion is real. If a developer is using a tool that hides the client-side cache and they keep seeing no data with a 304, they might think the server is broken.
When in fact, the server is just being extremely efficient. You have to remember that 304 is technically a success code. It confirms the cache control worked perfectly.
All right, now for the main event. This is where we spend most of our diagnostic time. The 4backx block. This signals a client error. The user, the browser, or the client app made a mistake.
And we'll start with the classic catch-all for a structurally poor request. 400 bad request.
A 400 signals that the server can't process the request because of a fundamental issue with the request format. It's about structural failure.
Right. It could be malformed, JSON a comma is missing, a parentheses is wrong, it could be invalid query parameters, or maybe the payload size was too big.
So the immediate diagnostic action for a 400 is to check the wire data. Verify the content type, lint the JSON, make sure all the parameters are there. It's usually a fundamental mismatch between the client and server contract.
Now we come to the most critical distinction in security communication. 401 unauthorized versus 403 forbidden. If you walk away with one key takeaway today, make it this.
Okay, let's drill down into 401 unauthorized. As the source material correctly notes, this should really be interpreted as unauthenticated. It's a challenge.
A 401 signifies that authentication is required, or, more commonly, that the existing credentials have failed. It signals a missing authorization header, an expired access token, an invalid signature. The server is politely saying, I don't know who you are, or your ID is stale.
So the practical distinction is clear. A 401 means you need to present valid credentials. The immediate action is to check the sign-in state, check token expiry, and debug that token refresh mechanism we talked about.
Now contrast that with 403 forbidden. This is an authorization failure. This user has already been successfully recognized and authenticated auth in the past, but they lack the necessary permission, role, or scope auth C. Failed to perform the specific action.
So they're trying to delete an account when they only have a read-only role.
Exactly. Or maybe they are authenticated, but the feature flag for the enterprise tier isn't enabled for their account. The practical distinction here is, I know exactly who you are, but the policy says you still can't do that.
And the diagnostic action for a 403 is completely different. You're not debugging the sign-in flow. You are debugging the permission model logic, checking the roles and scopes associated with that specific user ID.
This distinction is central to designing feature access and, crucially, to building upsell strategies.
Okay, next up, the classic 404 not found. The resource does not exist. But there is a huge security nuance here that product teams should understand.
Yes, the privacy nuance. To avoid information leakage. We said earlier that if a resource exists but you don't have permission, it should be a 403. But sometimes systems will intentionally return a 404 instead of a 403, even if the resource does exist.
Why the
It's about preventing enumeration. If the system always returns 403 for protected resources and 404 for non-existent ones, an attacker can rapidly probe your API to map out the exact structure of your database, valid user IDs, valid document IDs.
I see.
By returning 404 for both non-existent and unauthorized access, you obfuscate the backend structure. It makes it much harder for a bad actor to guess valid IDs. It's a security trade-off.
We also have 405 method not allowed. The endpoint exists, the resource exists, but the specific HTTP method you used, get, post, delete, isn't supported for that URI.
Simple enough. Now let's tackle the other pair that causes a lot of confusion, especially with forms and business logic. 409 conflict versus 422 unprocessable content.
A 409 conflict signals a conflict with the current state of the server. The request itself is structurally and semantically valid, but doing it would violate a rule related to existing data.
The classic example is a database unique key violation, trying to register a new user with an email that already exists. Or, more complexly, optimistic locking failures, where two users try to edit the same document at the same time. The server is saying, your request is fine, but I can't do it because of the current data reality.
I remember an incident where we had a critical 409 bug because two different microservices were trying to update the same user profile at the same time. We couldn't solve it with validation, and we had to introduce a lock. The trigger was always that 409.
And now contrast that sharply with 422 unprocessable content. In this case, the request is syntactically valid. The JSON is perfect, but it's semantically invalid.
Meaning the data inside violated a specific business or validation rule.
Exactly. The email field is formatted incorrectly, a number is outside the acceptable range, a required field is missing. The server understood the request, but the content failed a validation check.
And product teams should insist on 422 for form submissions because it lets the engineering team return clear, actionable, field-level error messages in the response body. This makes it easy for the client app to point exactly to the offending field,
Which is essential for a good validation UX.
Finally, in the 4XX block, the critical operational code. 429, too many requests.
This is the definitive signal for rate limiting. It confirms the client has sent too many requests in a given time frame and is being throttled. It's absolutely essential for managing resources, ensuring stability, and dealing with buggy or abusive clients.
And as a product manager for an API, you must specify the behavior around 429s. The client needs instruction. The industry standard is exponential backoff. The client has to wait increasingly longer before retrying.
Furthermore, the server responding with a 429 should include a retry after header, specifying exactly how long the client must wait. This is a critical product decision. Are we just showing a generic error, or are we building smart logic that reads that header and handles the delay gracefully?
All right, shifting to the final block. 5XX server errors. This is the domain of operational reliability, stability, and, well, incident response. These codes confirm the server failed. The client is absolved of blame.
The most common, and maybe least helpful because it's so generic, is the 500 internal server error.
The ultimate catch-all. It signifies an unexpected server-side problem, an unhandled exception, a code crash, a logic error that just wasn't accounted for.
When you see a 500, it usually means the operations team needs to look at application logs and tracing immediately to find the stack trace.
Next is 503 service unavailable. This one is specific and often temporary.
Right. A 503 means the service is temporarily offline. Maybe it's overloaded or undergoing planned maintenance. This is frequently used when deploying updates. You might route traffic to a 503 page while a new version spins up.
And crucially, like the 429, 503s are often paired with a retry after header. This tells the client exactly how long to wait. For high availability systems, both 500s and 503s should be treated as transient. The client should retry.
The final two codes in this block are vital for teams running microservices or complex architectures that rely on load balancers and API gateways. These codes tell you the failure point is upstream of the main application.
We're talking about 502 bad gateway and 504 gateway timeout.
Let's clarify the operational difference. A 502 bad gateway means the gateway or proxy, the entry point, received an invalid or malformed response from the upstream server.
A 502 often suggests a critical internal crash in the upstream service. Like if a container in your microservice architecture starts but then crashes instantly before it can send a proper HTTP response.
The load balancer will send a 502 because the response it got was fundamentally broken.
Conversely, a 504 gateway timeout means the gateway or proxy timed out while waiting for any response from the upstream server. The upstream service was alive, it accepted the connection, but it just took too long to process.
And that difference is huge for DevOps. A 502 suggests a crash or a health problem. A 504 strongly suggests a load issue, a performance bottleneck, or a long-running process that exceeded the timeout limit.
The service might be working, but it's just too slow. And as a product decision for reliability, 5XX codes should trigger internal resilience mechanisms, like circuit breakers, to stop hammering an already failing system.
Okay, now that we have the full vocabulary, let's synthesize this by running through a couple of real-world product scenarios. This is where the technical standards become actionable product design.
Let's start with scenario 1, login and session expiry in a high-traffic mobile app. This ties directly back to our access and refresh token discussion.
The scenario. A user is actively using the app, but their short-lived access token expires. What happens on the next API call?
That API call hits the server, which immediately sees the token is stale. The server returns a 401 unauthorized.
A set of good acceptance criteria dictates the response hierarchy. Level 1. The app must silently intercept that 401. Level 2. The app must attempt to use the long-lived refresh token to get a new access token. If that succeeds,
The original request is retried, and the user never notices.
the crucial product decision is the failure state. If the refresh token itself is expired or invalid, that silent level 2 attempt fails. The 401 response from that refresh endpoint is the definitive trigger that forces level 3. The user must be clearly redirected to the sign-in screen.
And maybe with a helpful message like, your session has timed out, please log in again.
The 401 is the technical alert that drives that whole seamless versus interrupted user experience.
Okay, scenario 2 involves permission changes and using a 403 as a revenue driver. We have a standard user successfully signed in. They can see the dashboard, but they try to access a premium feature like a bulk data export.
The export endpoint will immediately return a 403 forbidden. The system has validated their identity, but the entitlement checker confirms their role does not include the export scope.
And this 403 triggers a major product decision point. The technical response is simple. The product response is design work. You have 3 main paths. Path A, hide the export button entirely if they don't have permission.
Path B, show the button, but when they click and get the 403, just display a simple message: access denied.
Or Path C, which is often tied to revenue,
Right.
use that 403 as an upsell prompt. When the user hits the 403, the UI intercepts it and displays a modal. Unlock bulk exports. Upgrade to our professional tier now.
Or request access. Contact your administrator.
Oh.
The status code is not just a failure signal. It's an integrated component of the subscription model and growth strategy.
Let's discuss a classic engineering pitfall that product teams hear about but maybe don't understand the mechanics of. The CORS mystery options pitfall.
CORS, cross-origin resource sharing, is a vital security mechanism in browsers. If a web app on domain A tries to make a non-simple request, like a post with a custom header, to an API on domain B,
A cross-origin situation.
the browser doesn't send the real request immediately. Instead, it first sends a pre-flight request using the HTTP options method. It's the browser performing a security check, asking the API server, is it okay if I send a post from domain A to you?
And the pitfall happens when engineers say the request is failing before it even hits our business logic.
What's happening is that options pre-flight request is failing because the server needs to respond with specific CORS headers, like access control allow origin, explicitly telling the browser which domains are allowed.
If the server is misconfigured and doesn't respond correctly to that options request, the browser blocks the actual subsequent post request entirely. The server might have been ready, but the browser, enforcing security, killed the request on the client side.
Understanding that the options request is its own separate transaction is key to resolving those frustrating integration failures.
Finally, we have to talk about idempotency and retry behavior. This is a product risk topic that's masquerading as an engineering decision.
It's so critical for systems dealing with money or sensitive data. HTTP methods have properties. Get, head, and options are safe. They cause no side effects. Put and delete are idempotent. Doing it once or 10 times is the same result.
But the troublemaker is the POST request. PPOS is neither safe nor idempotent. It's used to create new things.
And why PMs care deeply about this. If you have an integration or a client that automatically retries requests upon failure, say, it hits a transient 504, and that request is a POST.
You risk double charging the customer or creating duplicate records.
Imagine a payment POST request succeeds on the server, but the server crashes right before it sends the 200 response. The client only sees a timeout, a 504. If the client auto-retries that POT, it sends a second identical charge.
That's a critical failure.
The mitigation is a product requirement, the idempotency key. You must require the client to generate a unique, one-time transaction ID and send it in the request header. The server uses this key to check if that specific transaction has been processed before. If it has, the server just returns the original result without processing the charge again.
So the technical property of the HTTP method directly forces the implementation of this mitigating product feature.
We've covered a tremendous amount of ground today, from the conceptual clarity of identity and permission right down to the specific, practical failures on the wire.
Let's quickly recap the non-negotiable distinctions.
For clear communication, always distinguish Auth, who you are, versus Auth, what you can do. And within the debugging hotspots, 401, unauthenticated, you need to sign in or refresh, versus 403, forbidden, you don't have permission.
And finally, 409, a conflict with the current server state versus 422, which is semantically invalid input data.
Understanding these codes transforms internal communication because they are diagnostic accelerators. When you see a 403, you instantly know the problem is in the role system. When you see a 504, you know it's a latency or bottleneck issue at a proxy. It's diagnostic efficiency.
And that leads us to our final provocative thought for you to chew on as you go back to your backlog and your requirements documents.
The language of status codes doesn't just describe system failure. It acts as a forcing function for critical product decisions, particularly around business models.
Think about it. Hitting a 401 unauthorized with an expired access token is a bug. It's a user experience failure that has to be seamlessly fixed with a silent refresh.
But hitting a 403 forbidden is often not a bug at all. It is a controlled, authenticated trigger that can be used as a direct path to an upsell, a prompt for an upgrade, or an access request flow.
The technical response code is merely the signal. The product response, how you recover the user, how you monetize the limitation, and how you ensure data safety. That's where the real design challenge and value lies.
The codes tell you what went wrong. Your job is to define how the user successfully moves forward.
That's a wrap on our deep dive into the hidden language of authentication and status codes. We hope you feel fluent and ready to debug effectively.
Go forth and write crystal clear acceptance criteria.